Swayam Prabha. Digital India. Educated India.
We introduced the diagrammatic perturbation theory in the last class, and we have seen how the diagrams could be very useful in calculating correlation functions, which then go on to expressions for impulse response functions, which then get plugged into suitability and station, which will emit radiation, and we have kind of spoken about linear response, second order response, but more importantly, we have also spoken about third order response, which happens to be most relevant, right? And we have seen, not explicitly demonstrated, but trust me here, the third order impulse response function can be written using 4 different correlation functions, right? With different interaction ordering, sort of. We call them R1, R2, R3, R4. And if you look closely, R1, so in general, third order response, as you can see, in a 2-level system, goes through a population term. The first interaction generates a coherence. Second interaction projects that coherence into a population. This is the coherence, this is the population, coherence, rotation, coherence, population. So the first 2 fields at the end results in a population. The third field interaction projects again this population onto a coherence, and this final coherence is what emits your nonlinear polarization or generates nonlinear polarization, which emits radiation. Now, something that you can already see, apart from the fact that the phase matching conditions for all these correlations are distinct and different, you can also see that R1 and R3 exclusively goes through the population in the ground state. So these 2 diagrams do not generate population in the excited state, whereas R2 and R4 goes through an excited state population. Right? Great. Happy with that. We have also seen how R2 and R4 either invert the phase of the coherence between the first and the last interaction, or keeps the same phase for the coherence between the first and last interaction. Accordingly, we have kind of termed it rephasing and non-rephasing. And these terminologies basically become evident because of specific expressions that we derive for these 2 specific excitation pathways. With one of them, if I kind of bookkeep the overall dynamic phase, which is kind of imparted into these 2 diagrams alone, and you will see that in one case, the phase is completely recovered, while as in other case, it is not recovered. And that comes from specifically the difference between these 2 terms in the expression. So that's why we call them rephasing and non-rephasing. Okay, all right. So let's dwell a bit more on top of this, how rephasing and non-rephasing kind of exists in the presence of severe bath interactions. But before I do that, I want to kind of move away from this time domain picture. So it's all in time domain, and we do indeed measure most of our response in the time domain, but we also eventually visualize everything in the frequency domain. That's a very important thing. So next we will, for today, we'll start out with what we call as a frequency domain representation, which eventually kind of originates from the primary definition sort of polarization. Frequency representation. Frequency domain representation, of course, here nonlinear. In this case, we are going to talk about only third order polarization. Of course, related to I3 is oscillating a signal has dependence on all three frequencies, the three interaction field and the amplitudes. Okay, remember that this frequency representation of your chi3 is simply a Fourier transform of your impulse response function. So if that I explicitly write that out, your chi3 is integral 0 to infinity d tau 3 e power minus capital omega 3 define those omegas at the moment, 0 to infinity tau 2 e power minus omega 2 infinity d tau 1 power not minus pi Fourier transform e power I tau 1 times, of course, the time domain response function, which we can develop using our double-sided Feynman diagrams. Here, your capital omega m's are simply the sum of energies. And of course, it kind of makes sense when you're doing response Fourier transform. When you are, of course, only with the first field interaction, you have to kind of your frequency axis is defined only by the frequency of the first field. If you have the second field, it will be omega 1 plus omega 2. You have a third field, omega 1 plus omega 2 plus omega 3. Variable. Okay, how will you kind of see this? If I'm looking at, for example, only R2, by the way, it's not omega 1 plus omega 2 plus omega 3. It is whatever the energy conservation is giving. For example, if I take only R2, which is K1 minus K2 plus K3, here omega 3, omega 1 minus omega 2. Right, so we all know how to write these response functions, correlation functions, for example. Let's redo this again for our R2, right? If I were to write that response function for R2, it's always good to kind of remember your Feynman diagram, which we had right here, right? Minus K1, K2, K3. R2, of course, minus 1 square, always remember that sign. Probability, you're going to come from the bra direction with the first interaction, so that will be mu 1 0 prime, your first dipole. Then the evolution along the direction of tau 1, that will be e power minus I omega 1 0 tau 1 minus gamma 1 0 tau 1. Gamma is the damping term, omega 1 0 is because with the first interaction you're creating a 0 1 coherence. After that, you come with the second field from the ket, so that will be mu 1 0 again, dipole, followed by the time evolution. In this case, now the time evolution is happening in the excited state population. So this is minus I omega 1 1 tau 2 minus gamma 1 1 tau 2, and of course omega 1 1 is 0. And finally, you also have another bra excitation, that will be mu 1 0 prime. power minus I omega 10 tau 3 minus gamma 10 tau 3, because you're projecting population onto a coherence, 1-0 coherence. And finally, after all the interactions, you multiply with another dipole and then take the trace, which is what we did. Right, so we should be able to write this out very nicely. And if you take a Fourier transform of this, analytically you can kind of already see how it's going to turn out, because you know if I have a time evolution like this, if I have, for example, your super operator, which is a time domain, this kind of function, take a Fourier transform, we know this already because this super operator acting on density matrix is going to give me a response which is going to go like this. The Fourier transform of that is going to look pretty simple. It's going to be a nice Lorentzian in the frequency domain. Right. Challenge here. You have 3 of such terms, so you'll have 3 Lorentzians. You have to keep track of your complex conjugate as well. So if I explicitly write that down, your kite 3 associated with number 2. Remember, I'm writing the final kite, which means I've already taken care of the complex conjugate of R2 as well. Just want to show you how one could derive expressions. It's kind of fairly simple. You have 4 dipole operators, so it becomes mu power 4. I have 1 Lorentzian associated with this interaction minus omega 1 minus I gamma 10 is my first interaction. The second interaction is acting from the ket 1 plus over omega 1 which is 0 omega 2 minus omega 1 minus I 1. Final one again complex conjugate, so minus 1 divided by 0 minus now omega 3 2 minus 1 minus I gamma 0. So that's analytical form for a 2-level system, third order nonlinearity associated with refacing pathway. The refacing pathway. So this is susceptibility associated with the refacing pathway for a 2-level system. I mean, for a 2-level system, it looks fairly simple and you should be able to write it out. But once you start having multi-level systems, this is going to get very clear. And in that sense, when we get there, we no longer deal with solutions. Still deal with analytical solutions. I can go on to 3 levels. Beyond that, better like you can or somebody else. Okay, remember that finally it's going to come to something like this, and that's what the key. Now, how we are going to represent this, what kind of visualization we can do, we will come back to that probably in 2 months. Most effective way of representing this happens to be a 2D. Okay, questions? Okay, so I already kind of said, we need to visualize this. Before visualizing this, we need to get some data. We need to be able to do some experiments. Right, let's talk about experiments now. So part of the experiment is we have this multiple pathways, R1, R2, R3, R4. How am I going to separate this out? Or is it possible that maybe I can never be able to separate? It would be nice if I can separate this out, because Those are going through very different coherent pathways, accessing different kinds of coherences as goes along as well as correlation. It will be nice to separate this out so that I learn something about inner details, inner workings about the material. It will be nice to separate this out. Can I do this? Can I separate, for example, rephasing and non-rephasing? Yes, of course, because you have the wave vector kind of conditions inherently given. Okay, so you can select signals by wave vector. So we can do this in two ways. We can do this in the frequency domain. But remember, there's also momentum conservation, there's also energy conservation. So you decide for a given chosen wave vectors, you decide frequencies along each wave vector. Those of you who have already kind of entered the ultrafast lab, you will see that we don't really tune frequencies. We take broadband pulses, have all possible frequencies at once, because that's what short pulses. You want to generate short pulses, and you want to have short pulses because you want impulsive response from a system. You want to give each field impulsively at very almost delta-like time scales, delta function-like time scales. You need to have short pulse. If I have short pulse, Fourier theory tells me I need to have a broad spectral bandwidth. So I can't really sit and tune my frequencies. That doesn't make sense. So because my measurements I'm exclusively doing also in time domain, I could select my signals by time ordering. Time ordering along vectors. Let's see an example. Let's say I want to distinguish between R2 and R4. I want to distinguish these two. I'm going to use my artistic skills. I thought I would make a PowerPoint slide, but I decided let me try out my artistic skills. I'm going to draw something here. Let's hope it works. So let's say I have three pulses, three field interactions, right? Three wave vectors. Let's say I'm going with my pulses along, and my pulses are traveling along axis of three vertices of a square, of a box. Okay, so first let me draw a box. And my three pulses here, starting three colors. This, and I'm going to a sample. That's my first pulse going there. Second pulse going there. So they should also end up in a box on the other side. Draw that box. Okay, so let's name this. Let's call this A. Let's call this KB, and let's call this KC. There's a reason I'm calling them A. And let's say I put my sample right in the focus. Okay. Now let's say I will look at for signal along the fourth vertex of this box at the opposite end. I'm looking in this direction. Let's say this is my K signal, And phase matching tells me this will be Ka minus Kb plus Ac. So whatever signal, if I'm seeing this there along the third vertex, that is coming because of wave vector matching of that form. Now I hope you don't have a problem with me saying that there will be a field emitted in that direction, because I have a sample. Sample, free field interaction, generates third polarization, is going to emit along all possible wave vector directions where phase matching occurs. This happens to be also one direction, and it will happen. You agree with me? Okay, now let's say I have this control of controlling which of these pulses come first, A, B, or C. Okay, time ordering. Okay, so I'll do time ordering. Let's do here. So let's say when A comes first, B comes second, C comes third. This is my time order. Then you will see a signal which will be K1 minus K2 plus K3. On the other hand, if I change my time order, let's say my pulse A is not coming first, it comes second, and before it, I make pulse B come. When I say pulse B, whatever is the pulse going along the KB direction is going to come first. Pulse is coming from A. B comes last. In this case, you will see K signal is minus K1 plus K2 plus K3. Remember, I'm always looking at the fourth vertex. I'm always looking at this point. And if you recall, this is a phase matching associated with my R4, non-rephasing, and this is a phase matching associated with R2, my rephasing. So I could build an experiment, 3 pulses that are coming in the so-called boxcar geometry. This boxcar geometry. Right. 3 pulses along the vertex. Now the digital tree. We have a diffractive optical. Right. The incidental on sample. I know my 4 direction. I could kind of determine that. Put a detector there. And whatever I measure happens to be the signal that I'm going to measure. And I'll do one measurement. In one first measurement, I will make sure my A pulse is coming first, and then B and C. And I get a measurement. Right? Then I take the time order and do second measurement. My first measurement will be the non-rephasing. My second measurement will be. Right? Yeah.
So these are ultra short pulses.
Yes.
So, I mean, you need to have some overlap in time, temporal overlap to generate the third order effects. So, what would it look like? The pulses look like in a time domain when you say first, second, third.
You don't need over. That's the whole point. That's the whole point of correlation function. It leaves some memory there. You excite, and system is evolving, and then you come with second, and then you have a second order. If you have a transparent, like take a BPO crystal, which is not observed, then you need to have all the 3 pulses overlapping to have third order generation. But if I have a sample which has a response,
Okay.
the whole point is that, right?
Right.
Free induction decay will exist.
Okay.
My system is still evolving, keeping the memory of the impulsive response that I have put in there.
So then experimentally, you'd have a certain repetition rate. So how would you go about? The pulses are still spaced over some period. So what do you mean by a first, second, third?
Okay, so there are 3 pulses. One pulse is coming first, second pulse, third pulse, right? And usually this difference you keep what? 10 femtoseconds to maybe 1 picosecond. Your repetition rate is like milliseconds. And you will scan this pulse. In fact, the way we do this is using in our lab, using a spatial light modulator. We control the relative, we phase cycle the pulses. In fact, in the reality, which we'll discuss later on, the way you actually do this measurement is through a method called heterodyning, where you have a local oscillator, a pulse whose amplitude and phase you have characterized or you know, and you let that interfere with the signal, and you measure interference. We'll talk about that, and because you want to have access to both amplitude and phase of the signal. Now a question for you. Let's say I set my time order to be this, to measure this. To measure the non-rephasing. A first, B second, C third. And I don't want to change the time order. Can I still measure with the same condition, even the rephasing signal?
One of them. We can add a delaying element in one of the paths.
I don't want to add delay. I want to keep. I don't want to change it. This is my condition, right? I have these pulses coming in a very specific time order. I'm not changing any time delay between the pulses. I measure the signal here. Cool. I have non-rephasing, but I have this flexibility for you to move the detector wherever I want. Can I measure rephasing? Remember, it's all about wave vector matching. You will, in this condition, this time order, you can go and verify this. You will see also a signal emitted somewhere along this line, and that will satisfy the condition for your R. So you just move the detector there you will find a field emitted by the rephasing susceptibility or rephasing polarization. So the reason I'm bringing this up is that it's not that when you are measuring non-rephasing with certain time order, suddenly you remove all the other responses. They're all there somewhere in space. You're just not measuring. Make sense?
For a given time ordering, we have all the processes there.
I mean, whatever satisfies this condition is happening. It's all there. It's nonlinear response as everything. It's only that the wave vector mismatch or matching happens to be in a different direction than where you're measuring. You get the point? For this particular measurement point, okay, this particular time order gives you the non-rephasing signal. So same time order, there is also rephasing signal emitted in that direction. Now we change the time order, rephasing will come back here. That's my point.
So geometry effect that we're saying,
Yes.
by which you're only getting that thing.
Yes. It's also background free, so you will see fields emitted in all directions, specific time. And this is true with nonlinear optics too, right? And it happens in that point. If you go slightly away, the efficiency, nothing is telling you that there is no field emitted in direction. Remember, the strength of the E field, emitted, is classical ENM, proportional to the polarization multiplied by a sinc function of delta K L over 2. The delta K is the phase mismatch, right? So in principle, if I go slightly away from this point, let's say go to a slightly different point, you might still measure something, some signal associated, emitted because of the polarization, but the amplitude of that will go to drop off as a sinc function. Like any other nonlinear process. we kind of figured out, okay, we can select signals by wave vector. Let's kind of go over different experiments which are typically done using third order response. See what unique observables it gives access to. The first thing that we start out with,
Just out of curiosity, like this sort of phase matching usually can happen with respect to liquids. Like you have for solids, you have this geometric phase matching where you just rotate the solid with respect to the different beams coming. With respect to liquid, I don't think so that's possible. Is it like more this phase matching if it's dependent on some other parameters like temperature or something? Will the same thing be there?
so always remember the phase matching is coming because of coherent ensemble that you're exciting. Even in the liquid, things are moving around, but when you come with the pulse, you're selecting a subset of this ensemble, which are all polar and they're all coherently excited. So in a sense, you're kind of freezing them in time, and that's what generates. And that's what generates the nonlinear polarization. So you can measure nonlinear response functions in gases. Because you're always this ensemble effect. They may be tumbling around, but not in this time scale. They're happening at much lower time scales. You're kind of capturing them, and that's what it is. Does it answer your question? Okay, the first experiment that we are going to talk about is photon echo, 2-pulse photon echo. Chemists in the room know at least one who's there. They will know spin echo, which is not that different from photon echo. Spin echo, in fact, this is historically nuclear magnetic resonances with NMR measurements, which estimate spin echo, kind of gave the original idea of performing nonlinear signals. All the experimental, let's say, methodologies, not exactly the implementations, but the spirit of the methodologies, as well as the theoretical kind of frameworks, have kind of been inspired by what people have done in the context of NMR, I suppose even in the 60s. Before. Okay, photon echo is kind of a very standard measurement to measure the phase. Okay. So in general, for a linear response function, let's write out the linear response function. I'm going to generalize this. Linear response, impulse response function in time domain. We have two-level system, e power minus I, 0, 1, the oscillating term, and a damping term. Till now I have been saying the damping term is gamma t, phenomenological. Let's say some function g of tau. Of course, it's a complex conjugate. This g of tau is basically capturing everything that you would think about. Now, if I have simply a defacing process leading to this homogeneous limit or decay of the coherence, then your g of tau, like we have considered so far, is gamma 0, 1 times tau. Okay, remember these microscopically, again, I have not developed the microscopic theory yet. Hopefully we'll do it in next class, Cobo-Anderson theory. But for now, we can kind of think of them, you generate the coherence and there are random fluctuations, stochastic fluctuations around, which is destroying the coherence, sort of irreversibly, getting lost. Right? Now, in addition to this, there can be slow fluctuations in the transition frequency itself for each ensemble. Not the coherence, but the transition frequency itself can oscillate. Right? That can be because of side-to-side disorder, local field fluctuations. There's nothing saying that the energy or the frequency of all my excitations is going to remain the same after my excitation, because each one is slightly different in environment, a small fluctuation. These are relatively slow fluctuations, some kind of disorder. This is typically referred to as inhomogeneous product. So how do you kind of capture this? So typically, now don't ask me how for now, next one we'll see. Typically these distribution of fluctuations in the frequency happens to have a Gaussian form with some standard deviation, let's say. Okay, this is some form. Okay. To get the actual functional form of G of tau, the damping term associated with distribution, at the end we have to evaluate sort of the ensemble average of the phase evolution. You agree with me? You have the phase evolution, and it's kind of calculating the ensemble average. You have some e power minus I phi of tau. Ensemble average will be giving you actually G of tau. That in fact is the starting point of where it comes from. Now if I have my omega of t of a single chromophore, let's say, is omega naught plus some standard deviation of t. Then let's say I let the chromophore evolve for some time, then I will accumulate a phase simply because of this fluctuation.
So this slow fluctuation can occur due to the perturbing field also.
Typically not. Perturbing field is instantaneous, right? It's done. It's gone after. I'm not, so at least in the context of spectroscopy, it's a short pause. The slow fluctuations happen at much slower times in that pause. If I had the light on continuously, probably, but then what kind of measurement? Right? The slow fluctuations are coming because of disorder. So let's say I let it evolve in some time and I accumulate a phase, right? And so that accumulated phase till some point tau will be integral 0 to tau delta omega of t prime dt prime. That's the accumulated phase because of my fluctuations. Basically phase, the dynamic phase of my state. That if I have something like that, then G of tau can be shown to be integral t1, t1, t2 of a correlation of these fluctuations between two different times, integrated over all time. How this exactly comes up, we'll hopefully see later. But for now, take this for granted. You can kind of intuitively see why. It's kind of correlating these fluctuations at different times, right? Over a long period of time till my tau, whichever my point of observation. Again, for slow fluctuations, there is a methodology called cumulant expansion, which again is something that hopefully we'll speak about, putting a lot of hope in you. But you can show that this correlation function can be evaluated half delta square tau square. So delta is your so your G of tau has two contributions. One from your homogeneous line width defacing process. That is basically what is destroying your coherence. And second, from fluctuations in the transition frequency. Two different things. Right? Both of them contribute to the overall damping of your response. And these are referred to as the homogeneous and inhomogeneous contributions. Okay. So now I can use this response function. I can calculate absorption spectrum A of omega. proportional. Let's not worry about the whole expression. The real part of basically is related to sort of the proportional to Fourier Laplace transform of R of tau. That's because we are first doing the Fourier transform of R of tau to estimate the chi, and then evaluating your emitted field from where you are calculating absorption. So it becomes a Fourier Laplace transform or a Voigt transform. So if I write this out, this will be e power minus I omega 0 1 omega tau minus gamma of tau minus half square t square d tau. That's your absorption spectrum. Let's take a situation where my delta is much smaller than gamma, which means my probability of fluctuation in transition frequency is much smaller than the damping coming from the defacing part, pure defacing part. If I do this, then you will see my line is a Lorentzian. And this, from here, you get the line width, you get the pure defacing part, which is related to the fact that you are losing the coherence that you have reached. We have another extreme where your delta is much larger than gamma, which means your fluctuations in transition frequency is much larger in amplitude and distribution than the defacing part. I'm not talking about time scales, I'm talking about amplitude, relative amplitudes. Then my line will be Gaussian, my absorption line will be Gaussian, and what you'll get out from here is only the inhomogeneous broadening. Now the problem comes in this pure limit, two extreme limits. At least you can estimate one possible, let's say, quantity. Okay, if my delta is much smaller than gamma, I know I'm measuring pure difference. Cool. If my delta is much larger than gamma, then I know I'm measuring inhomogeneous broadening, some quantity I'm measuring, right? Which is good. The problem, the headache comes when my homogeneous and inhomogeneous broadening are combined. Which is unfortunately the case with some of the, let's say, some of the systems that we work with. So the takeaway message is that I want to show you something. Share my screen. Simple Python code, nothing spectacular. So considering these three cases, and you will see that if I see the blue one is a very nice looking Lorentzian, and here I considered my defacing case, my gamma to be much larger than my sigma or delta. Okay. Now if I have my pure inhomogeneous, that's also nice. But if I consider them comparable, like phi and phi, it looks like a line shape. You can try to fit this with a Lorentzian or a Gaussian. You will not be able to fit in either case. Of course, you can force fit something, get a line width, but you will not be able to tell one from the other. And that is a limitation of linear spectroscopy. Okay? I can leave this code, I'll send this code, this Python notebook to you. You can play around with it. You can even try to fit this to a Bayes function and see what fits the best. And then you will know.
Can't they fit with two different functions?
Yeah, you can fit, and then I can fit anything mathematically, and then what is the precision of the numbers that I'm estimating. That's the problem. Fitting is good to some extent. At some point, there is imprecision or ambiguity in the parameters that are being used. That's the problem. Because they're so strongly intertwined.
But we know the functional form, right? Would it not just be possible to fit to that functional form since we know it's
This is exactly what I think. You have two fit parameters.
yeah, so it would be a two variable optimization.
Yeah. So we'll get multiple solutions. And you don't know. That's a problem. Okay. Let's go back to lecture. So this is void profile. You cannot really distinguish different contributions, homogeneous and inhomogeneous. So for kind of overcoming that, let's say we do a slightly different experiment. Experiment, I have only two fields. I have one input field. It's K2 and another K1. K1 first. And let's say I measure my signal. So this is the sample somewhere here. Focus. And I measure a signal. I'm drawing generically, but signal at a point where minus K1 plus 2 K2. This is sort of a special case for minus K1 plus K2 plus K3, where I'm combining now K2 and K3 into one single pulse called K2. This is what is referred to as a two-pulse photon echo. The tau 2 essentially becomes 0 because they are the same pulse. Write the double-sided Feynman diagrams for this. Can you write the double-sided Feynman diagram for this? So I can quickly draw this. 0, 0. Start here. Go to 0, 1. And I have my second interaction. But I also have the third interaction simultaneously. That's the right way of putting the Feynman diagram. And then of course 1, 0. Right, in this configuration, your R2 and R3 are exactly the same. You cannot distinguish them. Anyway, you know that the final signal will be oscillating at the frequency of omega 1, 0. And write 3, 1, 0. Now to write this. 1 power 4. 0. Power minus I omega 0, 1. I write the simplified version. Simplified version. You can check that, you can verify that my expression is accurate or not. But now I can expand this out considering various contributions to my G's. So to write that, write mu 0 1 4 0. It is easy. First term, I'm going to write minus I omega 0 1 tau 1 minus tau 3. But now let's say I also have inhomogeneous broadening, frequencies fluctuating, and what I'm measuring here is some sort of an average, mean value of omega 0 1. Yes. Then you are e power minus gamma 0 1 tau 1 plus tau 3. And e power minus tau 1 plus tau 3 square delta square over 2. That's homogeneous broadening. Okay, let's say I take the situation where my delta is much larger than my gamma, largely homogeneous. Situation, you can already see this function will almost become a delta function because you have this term here. I expand this out a bit. You will see that R3 has maximum at tau 1 equal to tau 3. Basically, the broad distribution of frequencies rapidly defaces during tau 1, but then rephased during tau 3. Don't understand it? Hold that thought. Let's go a bit further, because what we actually measure in practice, the signal that you are measuring is signal as a function of tau. Now, because tau is basically tau 1, there's only one delay between the two pulses, will be E signal square, which will be proportional to integral minus infinity to infinity d tau 3, because you are integrating everything after whatever is emitted after the third interaction. Okay? B of 3 tau 1 tau 3 square. And you can show that for this particular case, this will be mu 0 1 power 8, e power minus 4 gamma 0 1 tau. So I have what my experiment I'm doing is I'm coming with two pulses, right? I'm coming with one pulse, the other pulse. There is some delay between these two pulses, tau, and then I'm measuring some signal along a specific phase match direction, which is given by K1 minus 2 K2. And when I measure this as a function of tau, that signal, I signal, is going to decay. Its maximum at tau equal to 0 and then goes back. So where is the rephasing part here? So don't confuse the rephasing part now, because tau 3 you're integrating everything. That's very important thing. The thing is this: in the limit where my inhomogeneous broadening is going to dominate, is going to be the dominant factor. Think of, again, going back to a runner's analogy. Okay, runners start, each one is going a different rate. That is more equivalent to my frequency fluctuations rather than to a defacing process. The reason is this: I go back, and then I do and come back. It's completely reversible. The fact that it's completely reversible means that it's averaging to some value that you know, like fluctuations. And inhomogeneous broadening, it happens that your second pulse can rephase the entire thing back in the limit where my inhomogeneous broadening is the dominant one. When homogeneous broadening is dominant, then you are gone. Your phase is lost irreversibly. There is no way of making. And that's what happens here, that you are coming with your both the pulses, that both all the interactions at the same time, you have the maximum response because you're able to perfectly rephase everything. But then as you wait longer and longer, the decoherence kind of takes over, the dephasing takes over, and you will see it exponentially. Okay, it's an exponential. Note that this is a bit confusing, so I want you to kind of go back today, think over this problem critically, because in the next class, I want to kind of expand this out in the limit of where delta and gamma are comparable. And that where, in that situation, you will see that you may also have a situation where there is slightly a growth in the signal and then in decay. So there is kind of shift in the peak position. We'll talk about that in the next class. Okay? I want you to go back and think about this because I want to cover something else right now. So this is a very critical thing. I want you to think about it, then we'll come back, we'll discuss. Fair enough? But the important message is that in the limit where my inhomogeneous broadening is dominant, my 2 pulse photon expo signal is going to drop off at the rate of homogeneous broadening. So what I'm measuring here as my rate is directly the pure difference. So irrespective of, in the previous case, for example, when I do linear absorption alone, in this condition, if I measure the line width, what will I measure? I measure only the inhomogeneous broadening, nothing else. Here, magically, there's no magic, it's math, physics. You're able to access, looking at the dynamic of the 4-way mixing signal, access the pure dephasing rate. You're separating it out, you're eliminating the inhomogeneous. Okay, fair enough. Okay, let's go to a couple of other techniques that I want to kind of talk about. Mostly on probe, so that it's kind of out of our way. The next experiment, again, 2 pulse experiment. 2 pulse experiment. This is first pump probe. So I have 2 pulses again. Sample. I have my pump. And I have my probe. Let's call this KPU, KPR, pump and probe. And instead of looking at any random direction, we're going to sit right along my probe and I'm going to measure. So that's my phase matching condition. And you can write my K signal will be KPU minus KPU minus KPR. So there is no way with time ordering you can distinguish anything. Here you will see that all possible excitation pathways will contribute to your signal inevitably. You have no way to kind of separate out different functions. But what you are going to measure at the detector, what are you going to measure at the detector? Is some intensity. Okay. NC over phi, NC refractive index. EPR prime is a transmitted probe plus your E signal square. Unlike the previous case where we had only the signal, in this case you will have a signal as well as the unabsorbed or not absorbed probe. So it's not background free, it has a background of the probe. The previous case, the previous two cases we discussed, these are background free, only the emitted signal. Pump probe is a bit painful, but it's easier to do. So what you actually measure is not just intensity. The way you do pump probe is you have this pump chopped at some frequency. So you are modulating the pump. You collect a probe spectrum with the pump and without the pump, and you take the differential intensity between the pumped sample and unpumped sample. Okay. So basically, what you are going to measure is some kind of delta I change in the intensity induced by the pump. That is simply NC over 4 pi PR prime plus E signal, which can change with my pump probe delay, minus unpumped sample. So that's how you do pump probe. So under the weak probe approximation, this is kind of ubiquitously used. Usually in the pump probe experiment, your pump is much stronger than your probe. Probe is relatively weak. It's not exciting the system. It's not doing anything. It is of course interacting. Otherwise, there is no third order response. It's interacting, but it has what we call as a weak probe approximation. And under that approximation, you can write this out: NC pi prime signal plus complex conjugate where my E signal tau is of course related to your third order polarization. Fact show that my delta I of tau to omega signal L imaginary parts. Expand this out and show that imaginary part of the product, the probe field, and my third order polarization. Explicitly deriving this. Can be also shown that this can be even simplified further into more like a Beer-Lambert form as well. Change in absorbance. This direct link to the third order polarization. Right. So usually for analyzing pump probe spectra, you don't really invoke double-sided Feynman diagrams, write out all of this. Simply because if I write out my third polarization, you see all the possible correlation functions come in. It so happens that if I write them all down, most of them cancel each other, especially under relative long time scales, and you will see my delta I of tau is mostly proportional, of course, to mu 0, 1 over 4 e power minus gamma 1, 1 tau to the lifetime. Excited state lifetime, the population, gamma 1 for a two-level system. So because of that, pump probe is very powerful because it can really help you to track population dynamics. So I put some population and evolve, and you kind of see how it's evolving. There are various methodological signatures. And it's enough to kind of think about it only in terms of population without keeping coherences. I'll give you an example where coherences become important too in a while, a couple of minutes. Okay, let's see some typical pump probe responses, how it will look. So typically, as I said, the way to think about it is much simpler without anything. you have primarily three kind of response spectral features that emerge. Think of it like this: without the pump, your probe is going through. Of course, the probe has certain absorption, so that's your reference. You photo excite, you transfer some population to excited state. Now, because you have some population in the excited state, think of molecules, right? You're exciting some n number of molecules to the excited state. They are no longer available for absorption because they are photo excited. So when my probe comes after a certain time, you will see that the probe is not getting absorbed because there is nothing in the ground state to absorb. So this is what is referred to as the ground state bleach. Bleach the sample. Bleach because of the absence of the population in the ground state. Right? There's one feature, and usually if I'm doing a measurement of, let's say, in a transmission mode, it appears as a positive signal, positive change in the transmission. Measuring to a sample, there will be more probe available now because it's less absorbed. So it will appear as a positive signal. Now, depending on what is available, what kind of features are there, you could have some. Now we have population in the excited state. You could also have excited state absorption or photo-induced absorption. You can have open up new possibilities, new features. And so spectral regions, this is a spectrum as a function of lambda. So there may be some colors which are now suddenly getting absorbed. In addition, you could also have stimulated emission. So you have an excited state population. The probe photon, which is resonant with that, can come and stimulate a transition down. So you can also have a stimulated emission, which typically overlaps with your photoluminescence. The ground state bleach overlaps perfectly with your absorption spectrum. The stimulated emission overlaps perfectly with your photoluminescence. An example, this is a pump probe. The pump probe spectrum of MELPPP polymer is the name for it's a conjugated polymer. The reason I take it is kind of spectacular, but it's very well divided. So it has an absorption spectrum here, it's dotted line, right? With this feature here as absorption. And you do pump probe, you see a nice positive feature here. Okay, this is your photo bleach or ground state bleach, which matches with your absorption spectrum. Simply telling, my ground state is depleted, that's gone up, no longer absorbed. Now you also see a positive feature right here, just below the ground state bleach, and this overlaps reasonably well with the photoluminescence emission. So that's the stimulated emission process. The probe is going and stimulating emission. And you have a bunch of negative features here. These are all photo-induced absorption lines. Okay, you might ask, okay, what are all these absorption bands? Because you're only exciting system. So happens in the system, once you create an excitation, what we call a singlet excitation, photon can only create this excitation in the excited state will then evolve to different other features. In a molecule, it could evolve to be a triplet state. It could evolve to be a charged state, so on and so forth. The great thing about about this is that each of them has a very different, distinct absorption signatures. Like for example, here you have this PA here, which is associated with absorption of charged species. Okay, so you create a neutral species, but something happens in excited state and dissociates, creating charged species, and you can see signature of charged species. You can also see signature of your singlet state itself, what you photo excite, but you can also see signatures of triplets. Right? So in this particular system, you will see that your singlets at 400 femtoseconds delay, you have huge singlet states there, and also charge states, which means there's ultra fast dissociation of some fraction of charge of singlets into charges. But if I look at 400 picoseconds, then I see another very big, very large negative band here, which is associated with triplets. because triplets, intersystem crossing, takes some time. So I can kind of capture this kind of fields. Okay, and most of the pump probe basically is analyzing this particular way. We don't need anything beyond it. The biggest challenge in pump probe is that, okay, ground state bleach, simulate emission, you measure absorption spectrum, you already know where your spectral signatures lie. PA bands, you see a PA band. Now, as a spectroscopist, it's my job, especially for a new material system, to figure out what this PA band corresponds to. And that is not given for granted. You either have to use some kind of calculations, EFT or similar kind of calculations, to figure out what this might be, or do independent measurements. For example, if I want to know where the charge species band is, there's one way of knowing it. Just dope the system. Put charges there, see where they absorb. Then you know this band is a charge band. And there are other tricks that you can use to kind of figure out. But that's the job of another spectroscopist or any spectroscopist to assign these bands. And that is non-trivial. That's the point that I'm trying to make. And it's more very strongly a chemistry problem. All right. So
is it likely that stimulate emission can be high intense than the photo absorption?
typically it is not. Photo bleach is going to
Of
be
photo bleach.
photo bleach is going to be the dominant one. But there are cases which I have seen as well in some of our spectra. The stimulated emission optical gain is so high, the stimulated emission cross section is so high that that dominates. It can also be the ground state bleach is quenched because there is underlying photonews absorption which is pulling it down. That's all.
So in this case, the probe wavelength is
Probe wavelength is everything. It's a broadband probe. So 400 to 1 micron, you're probing the entire range.
probe laser is white lights.
White light continuum. Ultra short pulse, but broad. Okay, makes sense. Okay, one last thing that we can do now. We have seen ground state bleach, photonews absorption. Can we write double-sided Feynman diagrams for this? That's an exercise. Let's do that. Double-sided Feynman diagrams for ground state bleach. What could that be? You can choose one correlation. Doesn't matter which correlation you are looking at. Correlation functions. Because all of them will have. So one of the diagrams could be come with the pump. I'm choosing graph, kind of a refacing kind of thing. So I have one interaction here. I have also other interactions. 0, 0, both creating 1, 1. And let's say I have another probe field coming here. This projection 1, 0 goes down. This is your ground state bleach. Because you're going from ground state to a population projecting on a 1, 0 coherence, which exactly matches the transition frequency. That's where the ground state bleach lies.
So here the atom is already in the excited state, so it will start from 1, 1.
No, your pump is, this is the two pump interactions. Why is it an excited state?
Means the in the ground state bleach it showed the atoms are already in the excited state, and
So excited state is going this way. These are the two field interactions.
by observing the pump it is going to
Yeah, that's pump is the
Okay.
the one which drives the first two interactions.
Okay.
Right? Otherwise, you won't have three field interaction. 3 fields of your pump probe experiment, 2 fields come from the pump, 1 from the probe. Then we excited state absorption. So from 0, 0, 1, 1, be nice. I need to go higher. This is my probe. 2, 1. That's my PA.
Like stimulated emission at the same time.
So you cannot really distinguish from a Feynman diagram's point of view correlation functions. Ground state bleach and stimulated emission. They have similar signatures. Makes sense? Because at the end, both of them are kind of looking at 1-0 coherence. There is no way to kind of say that. We cannot, from a diagrammatic point of view, we cannot distinguish ground state features. Unless you kind of say, I'm treating a 1-1 population and that evolves to another population, kind of a Stokes shifted population, which then gives rise to emission. But that's a complicated way of saying things. But as I said, typically when you look at pump probe, you don't write out the Feynman diagrams and solve it. The reason I made you do it is because we'll kind of stop now because it's getting late. But next time we'll come back. I will show that even in pump probe, apart from population dynamics, I can also access coherences, specifically in a system where I not only have a ground and excited state, but also vibrational states. If I have something like this, I'll show that you can create vibrational coherences which will appear in your pump process as oscillators.
In 3-level system, with pump probe we can see the coherence also.
So typically, of course, you can generate coherence, but it's very hard to observe in pump probe experiments because of various excitation pathways interfere and kind of kill the coherence. In a very special cases, you can see. Sometimes you can see free induction, be careful in pump probe, but typically it's very hard. That's why you need to have 3 pulse experiments. The reason is again, you're combining all excitation pathways, and remember each of them can have different phase at -1 term. So sometimes similar looking diagrams can create destructive. And when you try to add all pathways, mostly you will kind of lose out on the coherence. So that's why it's very hard to see electronic coherence in a pump probe. You can see a vibronic coherence like this. That's a very different story. Does it answer your question? Okay, so the next class we'll start out with this is, by the way, the basis of resonance impulsive stimulated Raman scattering or impulsive vibration spectroscopy. It's kind of a very beautiful way of measuring Raman spectra in time domain. We'll start with that. Then we'll go back to our photon echo, kind of deeper into photon echo. Probably then into Kubo-Anderson theory, it's a microscopic response. Or you can also choose. No, let me choose. I don't want to give you too much. And then if we have time, then we'll start talking about 2D spectroscopy. Really start looking at how to think about 2-dimensional spectra, how to visualize this, show you some real things. Okay? All right, thank you, guys.